Now lately we've been getting a lot of emails from the fans out there asking us to explain how a Tesla coil works. So you asked for it, here it is. This is a Tesla coil with its clothes off, so you can see what the bits look like. Now the business end of the Tesla coil essentially is just a transformer. You can see I've got a secondary coil consisting of a lot of turns, and then a primary coil consisting of a small number of turns. So big turns ratio gives you a big voltage. But it's not enough just to have a transformer. In order to get those weird streaming effects that you see on YouTube or that you see in those plasma balls that you buy in the shops, you need to work at very, very high frequencies in what we call the RF range, radio frequency, so hundreds of kilohertz or more. So where are we going to get hundreds of kilohertz? We can't get it out of the socket, that's only 50 hertz. Well, that's what all the rest of this stuff does. What we have is we take our 240 volts, 50 hertz, stick it through a transformer. That transforms it up to 10,000 volts. We then pass that 10,000 volts into this thing here, which is called the spark gap. You can see that there's bits of metal with a gap between. That way you'll get sparks forming between them. We have lots of gaps because we want to get lots of sparks. On the bigger Tesla coils that you might see on the web, they have rotary spark gaps, and that way you keep rotating the electrodes so that you don't get the electrodes burning up. You spread the heat around so that they last longer. All right, why do I want to make sparks? Whenever you have an electrical spark, it sprays out a very wide range of frequencies. You can hear an example of this if you ever listen to an old-fashioned type AM radio and somebody's using a power tool nearby. The sparks generated by the power tool create a buzzing noise, a sort of, on the AM reception. And it doesn't matter what station you're on, because it's spraying out lots of frequencies, you're going to hear that noise. Okay, so now we have something that's generating frequencies, a whole range of frequencies, some of which are going to be in the RF range, up in the very, very high frequencies that we're interested in. But we don't want all those frequencies. We want to concentrate on one frequency. So we need a way to filter out all the other frequencies. And the way we do that is we have a thing called a tank circuit. A tank circuit is just a coil, or an inductor if you like, connected in parallel with a capacitor. And it turns out that when you have a coil and a capacitor in parallel, they will resonate at a particular frequency of electrical oscillation. So if you pick your capacitance and the size of your inductor suitably, you will then tune it to the particular frequency that you want. And you can see on this system here, I've got an alligator clip where I can tap off the coil at different points, so I have a different number of turns. And so I can then tune up my tank circuit so it only picks out that frequency that's generated by the spark that we're interested in. And because that frequency is now running in this coil, because that's part of the tank circuit, it's also acting as the primary coil of my big transformer. So I ended up with very, very high voltage, high frequency sparks. Oh, one more thing. Those of you that are electronics hobbyists may have actually used a tank circuit before. If you've ever made a crystal radio set, the tank circuit is the tuning circuit of your radio. That's the bit that picks out the frequency you want to tune into. You have a coil and a capacitor. And you could either have a variable capacitor, so you can adjust the capacitance, or you can adjust the inductance by tapping off, similarly, tapping off at different parts of the coil, similarly to here with this alligator clip. And in fact, up until fairly recently, all radios used a tank circuit in order to tune into the radio station you were interested in. I'd like to switch this on now and make a huge spark go to my head, but it's not actually working, so I'm sorry.